And for Z transforms, we talked about tables, properties, and symmetries. Remember that if your x of n is conjugate symmetric, that means your x of z will be real. And if x of n is conjugate antisymmetric, that means that your x of z will be imaginary. Otherwise, it'll be complex. And we talked about how to do that, how to take that inverse Z transform form. And we said, if you want an analytic solution, which is a formula, this is sort of the standard way to do it by hand. You're going to use partial fraction decomposition followed by use of the tables. If you want to do it by hand, numerically though, you'll do long division. Now remember, if you're going to do partial fraction decomposition and your ratio, the Z transform will always look like a ratio in Z, right? It'll always look like something along the lines of maybe with a Z to some power outside it. But then it's going to be this long factored mess. It might look something like 1 minus, I'll use the zeta symbol for Z to the negative 1 minus that zeta symbol, Z to the negative 1, and so on. And then underneath it, I'll use a lambda symbol. So its lambdas are its poles, and its zetas are its zeros. So our Z transform in general looks sort of like this ratio. In the example I gave on the other page, the denominator happened to be 0, which is the same thing as saying that its x of n is finite length. But if it has a non-zero denominator, then it will be infinite length. And if you multiply this thing out to create a one long polynomial in the numerator and the denominator, you can just directly divide them and pop out your first few numerical coefficients. You can continue to divide them as long as you want to get more and more numeric coefficients. If you're going to do PFD, though, with this thing, you'd have to say, keep the fact that there's a Z raised to something in the back of your mind, but now it's going to be equal to something over this first part plus something over this second part. Oh, I made a mistake. That should be Z minus 1. This is lambda 1. This is lambda 2. So each pole gets its own part. And then you do the cover-up method. But you first have to make sure that it's proper. And the way that I've drawn this, if I stop the dots with just here, it's not proper. The numerator is of m equals order 2. The denominator is also n equals order 2. And so you'd have to divide it out. And that we talked about how to do that in the partial fraction decomposition lecture. That's when you multiply them out to get polynomials, and then you reverse the order. So instead of saying from 1 and going down in orders of Z, you start from the biggest order of Z and you go back down to a 1 and do long division. We also talked about ways to do it using MATLAB. And in MATLAB, you use the residue Z command, excuse me, to do all this partial fraction decomposition work and to do the dividing out to make it a proper fraction for you. And if you need to get numeric answers, if you need to get a long sequence of digits out, you can use the filter command. And you'd use the, remember the filter is your your numerator and your denominator coefficients, and then followed by your input. And you'd use for an input, you'd use your you'd use an impulse. Because what you're really doing is you're pretending that your signal x of z actually represents h of n. And so you're transforming your numerator and your denominator of your z transform into the numerator and the denominator of a transfer function, and you're feeding it an impulse. And so the impulse response would have to be what your signal is in the time domain. All right, that's a that's a lot of stuff. I'll just remind you how the residue z works thing as an example. If x of z was 7.5 minus 25, whoops, minus 25, z to the negative 1. Using these touchscreen things, I have to slow down or else it can't keep up with my handwriting. So, Fawaz, what's the order of my numerator? What's my m here?
3.
Yeah. And similarly, my n is 2. So this is a second order signal, and it's, you know, you have to divide through. If you issued this command, with the numerator first, in decreasing powers of z, then denominator, whoops. It would pop out r is equal to 2.5 and negative 1. The poles are at 3 and at 2. And the coefficients after you divided it out to make it proper would be 6 and 7. And so that goes into showing that here's your coefficients after dividing it out, and the k vector, that's your k vector. Here's your r vector as the numerator. And there's your p vector. So from that, you can do the transform. Or if you wanted to find the first few values of it, you would say, you know, there's your numerator. There's your denominator. And if you wanted to find the first 101 outputs of it, you'd give it an impulse that's 101 long. Okay, there it is. That's a summary of everything we've talked about in 40 minutes and 50 minutes. And I think we're right on time to go. Before we go, I want to remind you, I'm going to give you the DTFT transform and table sheet. I'm going to give you the DFT transform and table sheet, and I'm going to give you the Z transform tables transforms sheet.